Hello. The next configuration we're going to see is that of a linear combiner DAC, which is also another popular DAC architecture. Notice that it consists of a linear combiner circuit. In this case, I have drawn an inverting linear combiner or adding amplifier, summing amplifier. It's all equivalent, with a feedback resistor, and then there are input resistors connecting the different inputs. Notice that all of the inputs are connected to the same reference voltage, negative Vref, via different switches, which I've labeled as V1, V2, all the way to Vn. The reason why Vref is negative is simply because this is an inverting linear combiner and I want my output to be positive, so I've added a negative reference voltage. My digital input word is basically what's controlling the switches, so my D will be the sequence of bits B1, B2, all the way to Bn, and each one of those bits in my digital input is going to control one of those switches, and therefore is going to connect that input signal or disconnect it. In the when the bit is equal to 1, the switch will be connected to the reference voltage. When the bit is equal to 0, that particular line will be connected to ground. And that for all the switches. Notice that B1 is my MSB, my Bn is my LSB, and my gain for each one of those bits or bit values is going to be largest for the MSB because my resistor is smallest, my input resistor R, and so my gain is always going to be RF over that particular input resistor. RF over R for the most significant bit, RF over 2R for B2, all the way to RF divided by 2 to the n minus 1 times R for my least significant bits. And so a larger weight is applied to the most significant bit, the smallest weight is applied to the least significant bit. Because this is a linear combiner circuit, I can express my output voltage Vout as being equal to Vin, which in this case is negative Vref, is the same input voltage for all the inputs, times the weights times the different inputs. So the weight for the first input is RF divided by R plus RF divided by 2R. I'm going to leave some space here. Plus all the way RF divided by 2 to the n minus 1 times R. Now notice that on those resistors that are connected at the input are only those for which the value of the particular bit is equal to 1. For those where the bit is equal to 0, they're just connected to ground, and so that line is effectively disconnected. And so in order to be more accurate here, I will have to multiply this times the value of the bit. So the first weight will be multiplied times B1, the second times B2, plus dot dot dot, and the final one times B sub n, my final bit. I can simplify this expression by taking RF and R, factoring them out of the equation. So I will have Vref times RF divided by R, essentially times B1 plus B2 over 2 plus Bn divided by 2 to the n minus 1. But just to make it more elegant and match the subscript on my bit to the power of 2 that I am applying, I'm going to go ahead and take a 2, factor a 2 out of my equation. So basically write negative 2 Vref times RF over R, and now will be V1 times 2 to the minus 1, as opposed to 2 to the 0 if I had the 2 inside the equation, plus B2, 2 to the minus 2, plus Bn, 2 to the minus n. So this is in essence the expression for my output voltage for the circuit. Notice that my full scale voltage is going to be equal to it's essentially going to be when that expression within the brackets, within the parentheses, b1 times 2 to the negative 1 plus b2 times 2 to the negative 2 plus, etc., when that expression is equal to 1. And so my full scale voltage is going to be approximately equal to 2 times Vref Rf divided by R. And the reason for that is I forgot to do this before, but Vref is a negative quantity, so when I apply a minus here, with the minus of Vref, this should be converted to a plus. So this will be my full scale voltage, but notice that my Vout max is always going to be 1 LSV below VFS, so my Vout max is going to be equal to VFS minus 1 LSV, where the value of my LSV is going to be equal to 2 Vref Rf divided by R times 2 to the negative n. That's the value of my LSB. Now, advantages of this circuit is that it is a simple circuit to design and build. It uses less components than the previous resistor array. The limitation of this circuit is that notice that the ratio between the smallest and the largest resistor is 2 to the n minus 1. So maybe I should write that somewhere. Limitation, largest R over smallest r is 2 to the n minus 1, which increases exponentially as n increases. And so at some point it will become impractical. I will have to use either very small resistors on the low end or very large resistors on the high end. And that's why there are other configurations that solve this.